Good evening one and all. This is lecture number 31 in electric and hybrid vehicle. This is professional elective number 3. We're in the last module, that is module number 5, and we have completed series hybrid drivetrain design. Today we are going to see the parallel hybrid electric drivetrain design, which is also called as a mechanically coupled drivetrain. Under the parallel hybrid electric drivetrain design, which can be found in the textbook of Ehsani in module 9 page number 255. Under this parallel hybrid electric drivetrain design, we are going to see the basic big system block diagram of the parallel hybrid electric drivetrain. We will see two types of control strategies. Same thing we have seen in case of series hybrid also. First type of control strategy is state of the charge, that is SOC control. Second one is engine on off or thermostat based control system. Finally, we are going to see the design parameters for engine, motors and peaking power source PPS. What is the speciality of parallel electric hybrid drivetrain? The parallel or mechanically coupled hybrid drivetrain has a feature that allows both the engine and the traction motor to apply their mechanical power in parallel directly to the drive wheels. In case of series hybrid electric drivetrain, we had seen that first the fuel energy is getting converted to mechanical energy by engine, then the mechanical energy was being converted to electrical energy. That was one source. Then there was battery, which was connected to DC to DC converter, and that was also giving electrical energy to the same bus. So electrical energy from the generator and electrical energy from the battery, they were getting connected or getting combined. Actually it is called electrical coupling, and then that electrical coupled energy or coupled electrical energy was being channelized to the motor, which was converting electrical to mechanical, and that mechanical power was being given to the final transmission system. In this case the fundamental is little different. In this case, instead of electrical coupling, mechanical coupling has used, and there are two types of mechanical coupling. One is called as a torque coupling, another is called as speed coupling. We have seen speed coupling is little more complex than torque coupling. So when using conventional energy system as IC engines as a power source, in that case torque coupling is more appropriate, since the IC engine is essentially a torque device. So among torque coupling and speed coupling, we have seen both these things in module number 4, second part. As long as there is an engine generator, or as long as there is an engine in the primary powertrain, it will be better if you are using torque coupling in the final transmission stage, because IC engine is also a torque developing device, and in that case torque coupling would be better. Major advantage of a torque coupling parallel hybrid configuration over series configuration: number one, generator is not required in case of parallel hybrid configuration. This is the main improvement in parallel hybrid compared to series hybrid, that is generator is not required. So one extra component is being removed from the whole drivetrain. Parallel hybrid requires a smaller traction motor compared to series hybrid. That means size of the motor is reduced, weight of the motor is reduced, so a smaller motor will be able to deliver required power to the final drive elements. So smaller motor and no generator, both of these things are actually saving space and saving weight of the vehicle. Last advantage is only part of the engine power going through the multi-power conversion. So a very small part of the engine power, not the whole, it is going for multi-power conversion. Hence the overall efficiency can be higher in case of parallel hybrid compared to the series hybrid. So whenever you are appearing for IA3, this question can be asked, that is why the overall efficiency of parallel hybrid is higher compared to series hybrid. So answers are given at the top, that is first, in parallel hybrid generator is not there, smaller traction motor is used, and only a part of the engine power goes through the multi-power conversion, not the whole power. But there are downsides. Control of parallel hybrid drivetrain may be more complex than that of the series hybrid drivetrain. That means control of series hybrid was easier, but efficiency of the parallel hybrid is more. So these two are the two advantages of series hybrid and parallel hybrid. Now, why the control of parallel hybrid is complex? The answer is because of simultaneous mechanical coupling between the engine and the drive wheels. So engine is directly connected to drive wheels through mechanical coupling. Hence, very good control of speed is not possible, or it becomes more complex. So in case of series hybrid, we knew that engine was mechanically decoupled from the wheel. So in that case, control was segmented. Better control could be achieved in a simpler manner. But in case of parallel hybrid, the drivetrain is having engine in one side, the other side is the wheel. Both are mechanical components. So as we are finding that engine is coupled to wheel mechanically, then the control of drive wheel becomes complex in case of parallel hybrid. So this diagram, you have seen type of this diagram in previous module also. That was a simpler diagram. In this case, a detailed diagram is given. So if the question is asked for 10 marks in the module 5 that explain parallel hybrid electric drivetrain, which is mechanically coupled. Now under mechanically coupled also there can come torque coupling and speed coupling, but that way we are not making this part complex. We are only showing the overall block diagram or schematic block diagram for parallel hybrid electric drivetrain. So configuration of parallel hybrid torque coupled drivetrain, it is mentioned here torque coupled because previous slide only we have talked that torque coupling is better because engine is a torque producing device. So many possible combinations of parallel hybrid drivetrain exist. Here we have taken one of many. So this design methodology for one configuration may not be applicable to the other. Each particular configuration may be only applicable for specified operation, environment and mission requirement. But as we are kind of new to this field, we are not directly from the mechanical engineering and all, we can see this diagram as a parallel hybrid electric drivetrain basic schematic, which is mechanically coupled, and the coupling is torque coupling as it is given here. So as in case of series hybrid, we found the input were coming from steering, accelerator and brake. The same inputs are coming here. This is actually called as operation command, and they are coming actually vehicle controller. This is ECU, that is electronic control unit, that is high-end microcontroller. There are two more microcontrollers. So microcontrollers or controllers are given in a red boundary. So engine controller is another you can say slave microcontroller, which controls a very important part, which is called as engine. It takes the input of all the engine parameters. Also it takes the input from the output sensor of vehicle speed. Though the vehicle speed sensor sensed input goes to the vehicle controller, but obviously this engine also has a link of this vehicle speed controller to itself. So depending on this vehicle speed, the vehicle controller tells engine controller that how much throttling valve, how much air vent has to be opened or closed. So that comes under engine control. Then there is another controller which is called as a motor controller, because we find that in case of parallel hybrid electric drivetrain, this engine is producing mechanical power. This is clutch gear system, so this is a power control. This is a transmission, and it is mechanical power given to the torque coupler. At the top you are finding this is a peaking power source. Peaking power source is nothing but the battery, and there are many measurements that are happening from the battery. So measurements are given by arrow. Here the peaking power source, that is battery, it's a BMS system. So battery current, battery voltage, battery power, battery temperature, all these things are continuously being monitored, and they are being sent to the vehicle controller, because vehicle controller should have total control on both the energy generating devices. One is engine, another is peak power source. Now this peak power source is actually giving the electrical energy to the motor controller, and through motor controller the electrical energy is going to the motor. Now this motor is also converting this peak power source electrical energy into mechanical energy. Now motor control is also being done by the vehicle controller. You can find this arrow. Vehicle controller is also controlling the mechanical brake, so anti-lock braking system, mechanical brake, and vehicle speed. All these inputs are coming to the vehicle controller. So for all the 4 brakes there are many parameters: brake fluid, regarding the brake pressure, regarding the cylinder. In brake there is a cylinder which is storing the viscous liquid. So all those details are sensed and continuously data is being thrown to the vehicle controller. So depending on all those sensed data, vehicle controller decides how much power is to be given to the motor and how much power is to be given to the torque coupler or in the transmission system. So it's a very heavily or very properly designed closed loop system where vehicle controller is the main head and engine controller, motor controller, they are the sub head. There are 3 links you are finding. So one link is electrical power link. So from battery to the motor controller to the motor, all this is the flow of forward directional electrical energy. So they are shown by dark lines. Signals, generally sensor signals for this mechanical brake, for the speed. Whatever signals inputs are coming to the motor controller, they are given by a arrow. Operation command is also a signal. So these are command signals. They are given through the sensor in accelerator, sensor in brake, sensor in steering. All those inputs are also coming to the vehicle controller. So the design methodology for one configuration may be applicable to the other. Each particular configuration may be only applicable to the specified operation environment and mission requirement. So whenever you are asked 10 marks for this question, you have to first explain vehicle controller, engine controller, motor controller, about these commands, and then you have to keep on explaining the internal part. There is peak power source, motor, transmission, engine and all, and finally you should talk about all the sensed parameters. So not all sensed parameters are shown here. Lot of engine parameters are sensed, that is what is the throttle valve, what is the air vent, closing and opening valve, their actions. Engine, you can say the crankshaft, rotational positional sensor, you can say that. So there is clutch gear also. So this clutch gear arrangement also you have to talk about, because there can be multi-gear system. So all those things step by step, point by point, you have to explain if it is asked for 10 marks, and a good neat diagram of the diagram shown here also has to be reproduced in the exam paper. So this is the main topic actually for today's session. So there are 4-5 slides. We will discuss few things about this block diagram. Design methodology of parallel drivetrain with torque coupling, which operates with electrically peaking principle, is shown here. So this peaking power source is nothing but the secondary source or battery, and engine is the primary source, which is mainly continuously generating the high specific energy for this vehicle to run. Peaking power source is only required when too much power is required from the vehicle during hill climbing or during very fast acceleration. At that time only this peaking source or peak power source or PPS comes into action. And there are 2 ways the engine can charge. There are 2 things the engine can do together. It can generate 100% energy. 80% energy may be used to drive the vehicle, and 20% energy may be used to charge the peak power source. So most of the time during charge controlling, during control of the whole drivetrain, one major aspect of this is to keep the peak power source charged as much as possible. So that is also the job of the primary power source engine. Engine is actually a easy thing, because we can fill it up by fuel, and we are having abundant quantity of fuel with us. So we'll just keep on fueling the engine, and the engine will keep on driving the vehicle as well as charging the secondary power source PPS at the same time. Some more theory. So here the engine supplies its power to meet the base load. So whatever is the vehicle minimum operating power required, that is called as a base load, which is called as operating at a given constant speed on flat and mild grade roads. So either flat load or very less grade, that means around 5 degree 10 degree inclination road, that is called as a mild grade road, or the average of the load of a stop and go driving pattern. So whenever there is a stop and go, so a lot of energy is wasted in generating the braking power. But at the same time, in that case, due to regenerative braking, the PPS can be recharged. So while regenerative braking, the mechanical power gets converted to electrical power, to the torque coupler, to the motor. In that case, the motor acts as a generator. So reverse direction power flow we find, and that power flow will come and charge the peak power source. So there are three conditions. So constant speed on flat road, constant speed on mild road, or average of the load of a non-stop, stop and go driving pattern. During all these three things, engine supplies its power to meet the base load. That means engine supplies its power to the axle or differential. From there, the power gets divided and goes to the left and right back wheel. Electric motor supplies the bumper power to meet peak load demand. It is actually a little controversial statement. Motor cannot supply power. Peak power source actually supply the power, but that is channelized through the motor. So whatever energy is coming from the peak power source battery, that gets converted into the motor electrical power, and that electrical power is given to the motor. Motor converts that into mechanical power, and this mechanical power actually gets coupled with the transmission power. The transmission is connected with the engine. So engine transmission power and battery motor power both are mechanical, because you find here there is a double line of mechanical connection. So these two are actually a double line, that means they are mechanically connected. They are actually connected to the torque coupler. Torque coupler then gives the power to the axle, differential and the wheels. The control system of the drivetrain consists of vehicle controller, that is the primary controller, engine controller, second highest command is there with engine controller, and electric motor controller, that is the third thing, and fourth is a mechanical brake controller, because brake is very important for any vehicle. So I had to put this thing also inside this red band, because this is also a controller. So in this diagram, whenever you will be drawing in the exam, you show this mechanical brake controller also in the control domain. So there are mainly four controllers: main vehicle controller, under this engine controller, motor controller and mechanical brake controller, they will be functioning. The vehicle controller is the highest level of controller. I told you this is the master control, and remaining three are the slaves. So the vehicle controller receives the operation command from the driver through the accelerator, brake and steering. One operating variables of this vehicle and its components are vehicle speed, engine speed, throttle position of the valves that goes to the engine, that means for valve for fuel, valve for air, and SOC of the PPS. So mainly we are tracking continuously the energy sources. So primary energy source is engine, which runs by fossil fuel, so all its parameters as well as all the parameters of this peaking power source, which is the secondary source. Controlling all these parameters are the main job of the vehicle controller. By processing all signals received based on the embedded drivetrain control algorithm design, the vehicle controller generates control commands and sends the commands to the corresponding component controller. So depending on the brake, acceleration and direction received from the driver to the vehicle controller then assesses brake sensor input, vehicle speed sensor input, brake fluid sensor input, and all other whatever possible, all those inputs, sensed input which comes at the input port of the vehicle controller. After measuring, after weighing all those sensor inputs, then vehicle controller tells engine controller what is to be done next, just to satisfy the demand of the driver. Component controllers includes or executes commands coming from the vehicle controller. So motor controller, mechanical brake controller, engine controller, they all are component controllers. So they wait from the vehicle controller to command them. So you are finding there is an arrow from here there is an arrow below, there is an arrow to the motor controller. So all these arrows are actually going from the main controller to the sub-controller. So the component controllers, which are sub-controllers, execute commands coming from the vehicle controller. Since the torque coupler is uncontrollable, so whatever is the torque coupler, it is uncontrollable, you are finding there is no connection between this torque controller to vehicle controller. Since the torque coupler is uncontrollable, the power flow in the drivetrain is given by this thing. So these two are primary power. So upper one is the secondary power train, the bottom one is primary power train. So since the torque coupler is uncontrollable, since the power flow in the drivetrain can only be regulated by controlling the main power source, which is the engine, traction motor, clutch and mechanical brake. So what they want to say is, after the torque coupler there is much to control. So output of motor, output of transmission, they can be coupled in the coupler, mechanical coupler, torque coupler, and then the generated power output is given to the wheels. So whatever control we have to do, we have to start generating the control from the starting part of the drivetrain, that is engine control, so engine output power control as well as the PPS power control. So this is what is told by the last paragraph, which is underlined. I think this is the last slide in this is the last slide in this block diagram. So important factors in drivetrain design are the power of the engine, motor, PPS and its energy capacity, transmission and the control strategy of the drivetrain. So these are the main things that we are supposed to control in case of parallel hybrid electric drivetrain. So what are those things? Engine, motor, PPS. So their capacity and design size, so their energy capacity, transmission and the control strategy of the drivetrain. So control strategy of the drivetrain mainly depends on the performance of engine, motor and PPS. So there are mainly 4 design objectives in case of parallel hybrid electric drivetrain. Number 1 is satisfying the performance requirements, that is the maximum cruising speed, acceleration and gradability, which are demanded by the driver. So that is the first and foremost requirement, that is satisfying the performance requirements, maximum cruising speed, acceleration and gradability as requested by the driver. Second thing, achieving high overall efficiency whenever possible. So efficiency means highest amount of displacement from one place to another with lowest amount of fuel and lowest amount of energy from the peaking power source. So we are going to spend least energy, stored energy, and we are going to cover the maximum length while driving. So having highest distance covered with minimum possible energy usage, that is actually called as highest efficiency. This is one of the major targets of parallel hybrid electric drivetrain design. So in one charge of the battery, in one fill up of the engine, vehicle should go as long as possible. Maintaining the SOC of PPS at reasonable levels while driving on highways and in urban areas without the need of charging the PPS from outside the vehicle. Very important thing, because this PPS mainly it will be like a batsman in T20 who will play for 3 overs and will score 50 runs. So they are not going to play throughout the match, they are not going to bat throughout the match. So it is, this peaking power source is required only when too much of power is required by the overall transmission system. In that case, the primary base power will be provided by the engine and secondary bumper power will be provided by the peak power source. Hence this third point, maintaining the SOC of the PPS, always we shall try to keep it above 70% at least. So lowest should be 70, highest should be 100. Always we have to keep this peak power source in fully saturated 100% SOC mode. So while driving on highways in urban areas without the need of charging the PPS from outside the vehicle. If too much of requirement is there, that means it falls below 70, in that case engine has to be started, and that will actually make the peak power source charge as 100. So we should not think of charging a peak power source from outside. We should make provision, smart provision of charging the peaking power source from inside only. This is the third requirement, that is SOC of PPS has to be maintained at any time, at any condition. And last one is recovering as much brake energy as possible. That means we have to design for this backflow of energy in terms of this regenerative energy. So all these four are main design objectives of parallel hybrid electric drivetrain design. Now in this case we are going to see there is a block diagram. So the available operating modes of a parallel torque coupled hybrid drivetrain, there are mainly 5 traction mechanism we can see here. I'm going to explain this 5 one by one. So first one is engine alone traction. Engine alone traction means the primary. So you are finding here this is the accelerator pedal signal, this is a brake pedal signal. So these two are the input signal. Left side is traction mode, right side is braking mode. So left side traction mode means you are taking the vehicle forward, and right side is braking mode. So I told you that there are two types of braking, electrical braking and mechanical braking. Electrical braking generates some kind of regenerative energy. Mechanical braking is all loss. So for engine controller, the job of engine controller is only traction. Motor controller is also traction, but engine controller generates tractive force by engine. Motor controller generates tractive force by means of electric motor. So engine power and motor power they get accumulated, and they actually produce the final power and gives it to the wheel. So motoring power and engine power. Motoring power is actually getting input from the PPS, and engine controller sometimes they come back and they charge the battery. That is also possible. Okay, so here the battery is not shown. Anyways, the motor controller is actually connected to the battery. So inputs are coming: accelerator, brake, and direction. They are given to the vehicle controller. It gives to engine controller, motor controller, both together. Primary and secondary. So primary and secondary sources they work, runs the vehicle. Right side is braking. So there are, I told you, two types of braking. One is mechanical and other is electrical. Electrical braking is also called as a regenerative braking. So it is generated by the electric motor. Reverse direction rotation of the electric motor compared to the traction produces the electrical braking. Electrical braking is high in amplitude, and we see that if there is very less amount of braking force is required, instead of mechanical braking, electrical braking is preferred, because in this case we are actually saving a lot of energy. So right side you are finding this is a mechanical brake power which is connected to the mechanical brake controller. So there is another microcontroller. So here actually 4 microcontrollers are shown: vehicle controller, engine controller, motor controller, and mechanical brake controller. So mechanical brake and regenerative brake or electrical brake can together together produce the combined brake power. So first one is engine alone traction. That means only the engine controller will act, and that will give the power to the wheel. Electric alone traction, that means the vehicle controller will tell the motor. From motor, power will go to the motor controller, electric motor will run the vehicle. So only the traction mode. Third mode is hybrid. An engine controller and motor controller together, they decide how much power will be produced by whom. Their power is getting added, and wheel is actually in a slope or very highly accelerating mode, but that also can be supplied by the third mode, that is hybrid traction or engine plus motor mode. Fourth one is regenerative braking. Whenever the vehicle is going downward, at that time regenerative braking generally happens, or whenever we are putting electrical brake, regenerative braking happens. We are actually saving some energy, and the energy backflows from the wheel to the PPS source. Last one is PPS charging from the engine. So PPS gets charged from 3 ways. One is during regenerative braking, it is getting charged from the wheel. Second is it can be directly plugged in and charged. And third thing, primary controller or primary energy source, this one engine power command, it can charge the PPS source. So this motor PPS, which should be somewhere here, so you can add a block here with motor PPS, and this engine. So engine actually through this whole process it can charge the PPS source. So this is the fifth one, PPS charging from the engine. So during operation, proper operation mode is used to meet the traction torque requirement, achieve high overall efficiency, maintain required level of SOC of the PPS, and recover as much as braking energy as possible. So these were the 4 targets we have seen, which were set in the previous slide also for parallel hybrid electric drivetrain traction. Now the overall control scheme is shown here. You can find the same thing was explained. It consists of the vehicle controller, engine controller, electric motor controller. So I can ask the whole control strategy of a parallel hybrid electric vehicle. you have to explain these two slides, and all the blocks you have to explain. So if I ask in control strategies, basic block diagram scheme wise, this diagram you have to show. Vehicle controller is the highest level, so I told you this is the master, and there are three slave controllers, which are engine controller, motor controller, and brake controller. So vehicle controller collects all the data from all the drivers and sensors, and from all the components such as the desired torque from the driver, vehicle speed, SOC of PPS, engine speed, throttle position, electric motor speed, etc., and so on. Based on this data collected from different sensors, the component characteristic and the preset control strategy and the vehicle control strategy all are decided. So vehicle controller sends a control signal to each component depending on whatever input it has received from different sensors. So each component controller regulates the operation of the corresponding component, like the PPS will be controlling the electric motor through motor controller. The brake will be controlled by the mechanical brake controller. That means there is a microcontroller which is controlling the brake, hence anti-lock braking system and all other things is possible in new age car. Engine controller will be controlling the valve opening closing, exhaust opening closing of the engine. All those things are very much required. So each component controller then regulates the operation of the corresponding component to meet the requirement of the drivetrain. Vehicle controller plays a central role in the operation of the drivetrain. Vehicle controller should fulfill various operation modes. We have seen some 8 to 9 operating modes for hybrid. In all those modes, vehicle controller is the main head. So vehicle controller will be collecting the commands from the driver. I told you there are 3 commands: acceleration, brake, and direction, and it will take all the inputs, it will analyze all the inputs. Depending on that, it is going to give command signal to the engine controller, motor controller, and mechanical brake, so that the other processes also run according to the driver's request. The control strategy in the vehicle controller is the key to success of the drivetrain operation. There are 2 strategies, as we have seen in case of series hybrid. Here also there are mainly 2 types of control. The first one is, or more complicated one, is maximum SOC of PPS control strategy. So we are supposed to keep the state of charge of the PPS, that is peaking power source, to the 100%. Always we have to try to do that. So when a vehicle is operating in a stop and go driving pattern, that means within the city, the PPS must deliver its power to the drivetrain frequently. Consequently, the PPS tends to be discharged quickly, because it is easier to control the start and stop of a battery than an engine. So whenever the vehicle is operating in a stop and go kind of a driving pattern inside the city, where frequent start and frequent stop are evident, in that case, more than engine, it is better to use a battery, because you can say switching on and switching off of the battery is much more easier than switching on and switching off of a engine. So as they are saying that in stop and go driving pattern in city, PPS must deliver its power. That means whenever the vehicle is in city, it's better that we turn on the secondary power source. Consequently, the PPS tends to get discharged quickly. Here, maintaining a high SOC in the PPS is necessary to ensure that the PPS can deliver sufficient power to the drivetrain to support the vehicle's frequent acceleration. So whenever the vehicle is running through the city, it is getting discharged very fast. But if we are then next trying to climb some hill, or trying to go through a very flat road but accelerate very high, every time we need a bumper energy source, and that bumper energy source is nothing but PPS or battery. Hence, whenever the vehicle is going in stop and go driving pattern, then also we have to keep our eye on the PPS. That PPS should be as much as charged as possible. If possible, PPS should be 100%. Basic rules in the parallel hybrid control strategy is using the engine as the primary power source, and as much as possible always try to deliver the power to the final driving element by engine, and at the same time charge the PPS whenever the engine has excess power over the required for propulsion. So whenever the vehicle is running through the highway with a flat road, at the time, if the vehicle is producing 100 watt, maybe 80 watt will be used for driving the vehicle. So use the 20 watt remaining power to charge the PPS. So without the PPS, SOC exceeding its full charge limit. So first we have to see how much is the requirement of the vehicle for driving itself on the highway on a flat road. If it is 100 unit, sorry, if it is 80 unit, then let the engine produce or primary source produce 100 unit. So 80 unit will be used for driving and 20 unit will be used for charging the PPS, as long as PPS is not getting 100% charged. As soon as PPS gets 100% charged, no need to produce 100 watt at that time. At that time you can produce 80 watt by the engine, and that will directly be connected to the final driving element. So in that case there is no PPS charging because PPS has already reached its 100%. So in this parallel hybrid control strategy with torque coupling, the maximum power curves for hybrid traction means electric plus engine alone traction, electric motor alone traction, regenerative braking, all these are plotted against vehicle speed. So there are mainly 4 graphs. Number 1 is hybrid traction, that means source 1, source 2 together with vehicle speed. Then engine alone traction, that means primary with vehicle speed. Electric motor alone traction, that means secondary with vehicle speed. And regenerative braking power with respect to vehicle speed. All these are very 4 important characteristics in case of max SOC of PPS control strategy. Power demands in different conditions are plotted. We are going to see all those characteristics in the next day. So point A, B, C, D, the operation modes are explained in a graph. The similar type of graph we have seen in series hybrid also. Today we are just going to see the graph and we are not going to do the explanation. So I will leave you now 1 minute with the graph. You just try to find out similarity of this graph of parallel hybrid electric driving with series hybrid electric driving. So I'm just giving you 1 minute. You see this graph, and after 1 minute I will give a brief explanation, and that will be the last slide we will control. So just check the graph of parallel hybrid electrical drive system PPS based control or max SOC of PPS based control. So just find out there are mainly A, B, C, D, E, F. In case of series hybrid there are 4 modes. In case of parallel hybrid there are 6 modes. So just see what are they. Okay, so you might have seen all the 6 different modes of this parallel hybrid electric drivetrain, and the scheme name is max SOC of PPS control strategy. Here the things to be observed. So though we are going to see it in detail in the next lecture, today I will give you a very brief description. So you are finding that there are mainly 6 operating modes. Number one is motor alone propelling, that means energy is coming only from the engine. Second is hybrid propelling mode, that means engine and motor both are using engine and PPS, actually they are giving the power together to the final drive element. Third one is PPS charging mode, that means PPS is getting charged. Now there are three ways the PPS can get charged. Which one is explained here we will see. So first is PPS can get charged from the primary source, PPS can get charged from the regenerative braking, and PPS can get charged from the external plug, that is also. But that thing is ignored here, that is we are not talking about external PPS charging. We are either talking of regenerative braking or we are talking about PPS charging from the primary source. So these are the three things. Engine alone propelling mode, that means only the primary source is propelling the engine. Regenerative alone brake mode. So there is a new thing which we did not see in case of the we had seen this also in case of the series hybrid. So there was a braking happening in case of the series hybrid, which was only a electrical braking. So that electrical braking was actually whatever we found in case of series hybrid. The same thing is there, regenerative alone. And hybrid braking mode, so this also we had seen, this was actually case D, sorry, this was actually case C in case of series hybrid. So series hybrid drivetrain, we found there was a hybrid brake system where electrical braking and mechanical braking, they were functioning together. So this regenerative brake, that means only the electrical brake, and hybrid brake, that is electrical and mechanical brake together. So these two were actually case number C and case number D. So whatever is E here, that was case number C in series hybrid. Whatever is F here, that was case number D in case of series hybrid. And above thing, motor alone propelling, hybrid propelling. So this hybrid propelling mode, this was case number A. The hybrid propelling mode was case number A in case of the series hybrid. And engine alone propelling, it was not there in case of series hybrid. PPS charging mode was not there. Motor alone propelling, this might have been there. So we are finding that this is kind of similar to the series hybrid, and here you are finding there are mainly parameters 1, 2, 3, 4, 5. There are 7 parameters. PL is the load power, that means how much power is expected from the both the sources to run the vehicle. That is actually called as a load power, traction or braking. Now from where it is coming, we don't know whether it is coming from only primary or only secondary or together from primary and secondary, that we don't know. So load power is actually the demand power. Whatever is the demand of the power from both the sources or from the drivetrain, that is actually called as a load power. PE is the engine power, PM is the motor traction power. So PM is actually coming from the PPS. PMB, so B stands for brake, PMB is the motor braking power. So this is nothing but the electrical braking power, PMB. PM stands for motor power, B stands for brake. So brake motor power, that means this is actually the electrical brake power. So for electrical braking, actually we are taking some energy from the PPS also, that is the battery. PMC, PPS charging power. So this PMC can be done by the primary source, as well as it can be done by regenerative braking. So PMF, mechanical braking power. So PMB and PMF. Okay, so this is mechanical braking and this is electrical braking, PMB and PMF. VEB, this is the vehicle speed corresponding to the engine minimum RPM. So VEB is the vehicle speed. So these are the parameters, that is load power, engine power, motor traction power, that is the secondary source power. PMB is the braking power, PMF is the mechanical brake power, PMC is the PPS charging power, and lastly VEB is the vehicle speed. So these are the parameters you can see in this graph. This graph is also having two regions. It is exactly cut by the baseline or zero speed line. X-axis is speed, Y-axis is power. Now the power is having two power. Above zero axis is traction power, which is taking the vehicle forward, and below zero it is the braking power. Okay, and we are having that there are mainly 5 modes here, 5 cases, 1, 2, 3, 4 and 5 you can find here. 1, 2, 3, 4 and 5, there are 5 positions. and the 5 positions are maximum power in hybrid mode, that is this graph. Okay, so cases are the same, cases are A, B, C, D only, but there are 5 graphs which are shown here. Those graphs are explained first. So after just explaining these 5 things, we will stop. A, B, C, D are same. So this is A, where actually hybrid traction is taking place. This is B, where only engine based traction is taking place. This is C. So C and D are exchanged here. In the previous case, C was combined brake and D was brake only by electrical. But in this case, C is the brake only by electrical, that is only PMB will be acting here. You are finding that is demand brake is same as electrical brake. That means whatever is the brake demanded, that will be satisfied only by the electrical braking. And D is actually the combined or hybrid braking, which is nothing but addition of the whole thing. This is the demand brake power, which is actually coming from the MF and MB. So PMB is the electrical brake and PMF is the mechanical brake. So D and C already explained. A, you are finding A is a very hybrid, so PL, total load. So total load is exceeding 2. What is 2? Maximum power with electric alone traction. So this is only electric. What is 1? Maximum power in hybrid mode. So from below to here, so from this 0 point to this 2, this much power can be the maximum power by the PPPS. Okay, and 2 to 1, this peak, this is actually the power which is from the here it is written, so 2. So this 2 is nothing but maximum power with the electric alone traction. That means this baseline to 2, this is actually power coming from the PPS. And from 2 to 1 peak of that, this is actually power coming from the engine, you can find here. Okay, so we will see actually this thing in the next day, and we are going to see how this A, B, C, D, all those 4 things are happening. So you also, if you just go through, you will also understand the same thing, or don't worry, next day we are going to discuss it in detail. So this was a starting lecture of hybrid electric parallelly coupled or mechanically coupled drivetrain with torque coupling. So next day we are going to go in detail about these various operating modes based on the power demand. So this graph will explain, as well as there will be a flow chart on this max SOC of PPS control of electric hybrid drivetrain with parallel with torque coupling. So all those things we are going to see next day. Till then, it is good night and goodbye.